An Introduction to Molten Salt Reactors Safety Assessment. Molten salt reactors, MSRs, are characterized by either the coolant or both coolant and fuel consisting of molten salts, typically fluorides or chlorides. From the safety point of view, the MSRs differ significantly from the light water reactors, having many features which make the use of the traditional classification of safety barriers, core damage states, and accident sequences of little use when assessing the safety of these reactors. Severe accidents, for example, have been typically characterized as showing a considerable degree of core damage and a fraction of the core in a molten state. In many MSR designs using a molten fuel, this classification cannot be applied. The ultimate safety goal, however, remains the same in all nuclear reactors. That is, to ensure reactor operation without an unplanned release of radioactivity so as to threaten humans or the environment. The absence of a fuel cladding and the presence of a large fraction of radioactive material, not only in the core but also in auxiliary systems, such as an off-gas system and fuel treatment facility, make MSR distinctly different from light water reactors when regarding the confinement of radioactivity. As in any nuclear reactor, the formation and transport of radioactive vapors and aerosol particles play a key role in the source term evaluation during severe accidents. In a typical light water reactor, most of the fission products transported in the reactor coolant system will be in particulate form, with the exception of the noble gases xenon and krypton and iodine, which can form molecular I2 or organic iodine compounds that exist in the vapor phase in the containment building. The behavior of fission product compounds depends, for example, on the concentration of the different species and on the thermal hydraulic conditions, such as temperature and pressure, of the reactor coolant system and the containment. Less information is available on the forms of fission products released in an accident situation for more advanced reactor types, for example, Generation 4 reactors. However, the expected form of transport would in all reactor types be as an aerosol with varying fraction of gas phase compounds depending on the gas composition and temperature. In an MSR, the fuel can be dissolved in the salt that also acts as the reactor coolant. Because of its different design principles compared to light water reactors, the release of radioactive material in an accident in the molten salt reactor cannot be determined based solely on the knowledge of light water reactor accident source terms. Only limited experimental data are available to support source term assessment from molten salt reactors. In addition, a large number of different molten salt reactor designs and salt compositions make it difficult to apply data developed for one reactor type to another one. The molten salt reactor experiment showed that very small amounts of fission products were released from the reactor during the operation of the reactor. However, accident conditions were not tested. In the absence of experimental data, analytical tools have been and are still being developed to estimate the release of radioactive materials from molten salt reactors under postulated accident conditions. The European project, Simulation Models and Safety Assessment for Fluid Fuel Energy Reactors, Samosafer, aims at developing and demonstrating new safety barriers to control the behavior of molten salt reactors in severe accidents. Samosafer is a continuation of various activities undertaken in Europe to investigate and develop an MSR. These activities started in the early 2000s with a concept derived from the American molten salt experiment. In Samosafer, new simulation models and tools are developed and validated by experiments. The reactor under investigation in Samosafer is designed with a fast neutron spectrum and will be able to be operated in the full range from breeder to burner reactor. This flexibility is facilitated by the fact that the fuel salt composition can easily be adapted during the reactor operation without manufacturing solid fuel elements. During reactor operation, a fraction of the salt is continuously diverted into an X-core salt cleanup unit to extract lanthanides and actinides. In this work, evaporation of fission products in salt compounds during a hypothetical MSR accident in which the fuel salt is drained from the fuel casing onto the floor of a confinement is analyzed. The confinement is under a nitrogen atmosphere, and the fission products and salt material are evaporated from the surface of a molten salt pool, which is formed on the confinement floor. In the absence of a detailed confinement design, a generic, very much simplified confinement geometry is assumed. Thereby, the conditions of the present investigations can be considered as generic bounding conditions in which the detailed design of, for example, storage tanks are not considered. Inclusion of the detailed geometries, once available, is expected to affect the release of fission products and salt materials, in addition to the release of radioactive materials from the fuel salts. The formation of aerosol particles in the modeled confinement is investigated.